It's always listening.
The aliens are listening.
Yes. Good morning, Mr. Britt. Mr. Giles, how are you?
I'm doing good, yourself?
You know. Morning, Dr. Ryback.
Hello.
Why is-
That is disrespectful.
Look at your bright and shiny faces on this camera here. No, never.
I have Mr. Peppers. Yes, Dr. Peppers, you are here. We have about 2 minutes, and then I would like 1, 2, 3, 4, 5. We're waiting for one more site. Ms. Diaz is who we are waiting for. So once she gets in, Dr. Peppers here, within the next 2 minutes, I need you to go ahead and get started for us and make some introductions around the horn for us. Unfortunately, I will have to step out. We might have some kind of a emergency drill around 9:30 time frame. So Ms. Poe can volunteer to step in until I get there. You have 1 minute, Dr. Peppers, so stop handing out papers. All right, Dr. Peppers, it's all yours. Please take over and let's get some introductions for us.
You're muted.
Got it. I'm back to this technology again. It's gonna get me one of these days, I know. But welcome to our CGS dual enrollment chemistry class. I'm Dr. Peppers, and I do like to drink Dr. Pepper, so no big deal. Also, I'm the adjunct right now for Richard Bland College. So as you pay for the enrollment, you get 4 credit hours in chemistry. I know your teachers already talked to you about that, so I'd encourage you to go ahead and do that. It's really worth it. unless you get a D or lower, which hopefully nobody's gonna do that, right? Anyway, I grew up always wanting to be a mad scientist, so I became one. And then later, I decided I wanted to teach high school when I retired from my biotechnology job. And I've been here this is my 14th year. So I'm glad to be here. I'd like to hand it over to another teacher. Let's go with Paul Reebok. And then when all the teachers have been on, let's give it back to Mr. Garrison, and he's going to lead us in the broadcast.
Hi, I'm Dr. Ryback. I'm at Colonial Forge, and this is my 4th year teaching in CGS. And I'm actually a chemist, retired chemist, that's gone back and started teaching. So welcome, everybody.
Okay, go ahead, Ms. Pogue, go ahead and take over.
I'm Jennifer Pogue. I have been part of CGS for, this will be 16 years. And I am at the Stafford site.
All right, Ms. Diaz, would you mind to go ahead?
Oh, no, I just got, oh, there I am. I'm Mr. Britt. This is my first year at CGS, but not my first year in science. I love chemistry, and it's gonna be an awesome year.
I'm Miss Diaz. I'm over at North Stafford. This is my, good grief, can't even do math this morning. 4th year, full year in CGS, and I am working on my chemistry master's.
I think that just leaves me. I am Mr. Garrison, 15 years in the program, and we have to get ready for our fire drill. So let's at least share our screen here and let's get started with the presentation. Very good. Thank you, Ms. Pope, for that help there. And so let's see if I have. So that means I think you are controlling the screen then, Ms. Pope. So if you want to, I've still got a couple of minutes here, but so today's goal, I've got 2 things that I want to share with you. Ms. Pope's going to help us out on this one. I want to take you through the history so that you can understand, or so that you can learn some of the people's names that are out there and in her class. These are all the students that are in CGS, I assume here.
Oh, gosh.
That's okay, that's okay. So, I know, so, let me see if I can take over here. There, I got it. You're gonna have to take over here in just a second. Okay, so, 2 goals. I want to take us through the history of the science of the atom, so that you can learn how we eventually came to this idea. We all take it for granted that there are protons, neutrons, and electrons. How did we get to that level? Where did it all come from? So we're going to take you through a few of the prominent scientists that got it there. And then we're actually going to start breaking apart that atom, and we're going to be able to calculate by the end of the day how many protons, neutrons, and electrons there are given just the name of the element. So let's go ahead and get started with what is the most basic idea behind the idea of matter. Well, there's a fabulous video that we'll have to share with you at some other time. Here's what you need to know. If we understand this basic idea, and it took us, you're going to see from the history, 2,000 years to get to this point. I will be back. Ms. Pogue, we're in charge.
Make sure you unshare your screen so I can move forward.
He's gone. He's gone.
Actually, I think I can override it. Okay. So if someone at another site can just double check that you're seeing where he left off and hearing me.
Looks good. Everything's
Okay.
good.
So matter by definition means that whatever it is taking up space, okay? And it has mass. You have to have both things. So when we quantify matter, we're saying that it has mass and it takes up space. That's where we get that whole idea of density. Has mass, takes up space. There are lots of things that don't, that cannot be labeled as matter. Time being one that's most common. You're very familiar with the 4 states of matter. So what we need you to understand in a solid is that it's a regular repeating pattern of the atoms. All that the molecules can do, all that the atoms can do is vibrate in place. Okay. And so what happens with that is it sits and it will sit in its spot and just shake. Okay. I'm going to go out on a limb and just do some stereotypical analogies for you. Think about this as the fashionista's suitcase. How many of you know the trick of rolling your clothes to get more into your suitcase? Right? And then we have the trick of we're going to stuff socks inside our shoes, right? Because we want to get that stuff as tightly packed in that suitcase as we can so that we can take the extra whatever. Does that make sense? That's a solid. Okay, all that is going to happen inside that suitcase is the items are going to vibrate. They're not going to move around. When you open your suitcase, it's going to look exactly the same way as it did when you closed it. Does that make sense? That's a solid. Liquids are things that have defined volume, but not a definite shape. Okay, so a liquid is going to take the shape of its container. Sometimes it actually interacts with that container. When we're looking at measuring water in a graduated cylinder, we have to get down and look at the bottom of that meniscus, the curve, right? Because there are actually forces between the water and the graduated cylinder that cause the water to not be a straight line. Okay, your liquid is going to vibrate. It has a little bit more motion. They can slide past each other. Think about this as like pearls on a necklace. Okay, they can vibrate in that location and they can spin in that location, but they're not totally free to move on their own. You with me? Gases have no definite shape, no definite volume, so they are going to actually expand to take the space that's available to them. If we had Pepe Le Pew make an appearance at your doorway, we know who Pepe Le Pew is. Yes. Some of you don't know that Pepe Le Pew is the skunk in Looney Tunes. That makes me very sad for you. Yeah, you go home and watch some Looney Tunes as part of your downtime. So if you had a skunk that came in the door, we are very clearly going to smell that skunk close to the skunk, but it's not going to take very long for that odor, the gas, the molecules that are the smell, to expand to fill the room. If you've ever had a dog have an unfortunate encounter with a skunk, you know that you can smell that all throughout the house for a long period of time, right? Until those molecules get dissipated. Plasma, we don't talk a lot about plasma, okay? They're going so fast that the electrons are ripped off. We're not talking about plasma television. We're not talking about plasma screens. That is named after how the crystals kind of move like the plasma in your blood. This is a different state of matter altogether. Okay. I want to go forward. Thank you. So Democritus was the first Greek to actually kind of qualify what we were talking about. He was the one who used the term atomos, where we get atom, to say that everything can boil down to something that is indestructible. An atom is indestructible, it's indivisible. But we don't have any data to support that. But he was the first one to say atoms exist and they can't be divided. That's what I would write down. Atoms exist, they can't be divided. He did his work in 400 BC. So we don't really have much to go on, but it was a starting point. Aristotle came next. And he actually said, well, we've got 4 types of atoms. Earth, air, wind, and fire. Yeah, maybe in a band, right? And again, he didn't really have any experimental data. He just said, we're gonna say that everything is made up of earth, air, wind, and fire. That's what they believed constituted everything back then. Okay, I'm going too fast. I'm sure you guys will. So earth, air, you get it. That's the band, yeah.
Whoa.
Hey, the 70s were a groovy time, okay?
That is more than just the band. That is an experience. All right, I'm gonna take over in just a second. If you can do one more slide for us until my kids come in, go ahead, but we're
Okay.
almost ready.
So then we had Robert Boyle. Fast forward almost 2,000 years. So we were with Aristotle and Democritus back in 350 BC. Now we're in the 1660s. Robert Boyle actually collected data. And what he found is that these atoms will combine to form other things. Okay. So we have different kinds and shapes and sizes. He called them corpuscles. And that they recombine or combine to make new things. But he was really one of the first who had data to support his observations. And as we know in science, data is really what drives what we know. Are you ready, Mr. Garrison? No, okay. So Antoine Lavoisier came next. I'm probably not saying his name correctly. That's okay. He doesn't mind. He showed that matter is indestructible. He actually had data. He had scientific proof. And he also said that matter is going to have constant mass. Okay. Some other interesting tidbits that are not quite as important. He helped create the metric system. Maybe that makes you happy, maybe that makes you sad. And he was the first to try to standardize how we name molecules, how we name combinations of the different elements. So in about a month or so, you probably will be cursing him quietly to yourself, not out loud, of course, because we will get into how we name compounds and molecules.
Okay, I'm ready now. We are back in the classroom. My kids are all well rested and they are feeling like they have had an adventure, their first field trip. Guys, how excited are you about Philadelphia field trip? I hope that you are really, really pumped that this is going to be a great event for you and for the program. Okay, so where we leave off with Antoine Lavoisier is that he understands that through experimentation, we cannot break up the atoms, and that if we put them together, they will make specific molecules. And so he comes up then through a series of experiments saying, no matter how we do these experiments, I come up with the same results. And if I put a lid on the gas, I can trap it and I can keep it. And so he has developed this law of conservation of matter, conservation of mass. It says whatever you start with in a reaction, that's what you're going to end with. So if you can do a reaction in a closed container, the weight of the container will not change, even though the materials inside will change, such as we have methane, which is your natural gas that comes out of your stoves. If you ignite that, it's going to make carbon dioxide and water. And he was able to prove that if he traps gas and ignites it, that he would be able to produce the exact same weights. It's just new products. So he was able to test before and after to prove that they were new products, but that their weights did not change. Coupled along with that, then, a few years later, we have a gentleman named Proust. And Proust comes up with now further developing his ideas of Lavoisier, saying that this is the law of definite proportions, meaning it doesn't matter if I have 100 grams of carbon dioxide or if I only have 1 gram of carbon dioxide. The percentages are going to be the same because the formula is the same. It's always CO2. So it doesn't matter the amounts, the ratio of carbon to oxygen atoms will stay the same. So this is, again, we're just advancing in our understanding of the atom. These are the baby steps towards it. So we're right at 1800s. Now we get into the new century. John Dalton. This is where we really want you to focus and start knowing their names. John Dalton comes up with the atomic theory. Now, at this point, you've heard some history. For almost 2,000 years, we've known that atoms are indivisible, but no one gave them a name. So here we have now, John Dalton comes up with the idea of the atom. I believe he is taking his influences from Democritus at the start there, Atomos. And so here we have John Dalton now officially declaring the smallest form of matter that we could know at that point called atoms. So he also did a little bit of work and he started to discover a few elements and he started to deal with standardization of the namings. But what we want you to understand is that he comes up with the idea that there are atoms. His law, which sounds so similar to the law of definite proportions, well, now we have the law of multiple proportions. And it says that just because you deal with carbon and oxygen doesn't mean you're always going to make carbon dioxide. There are different compounds with the same elements. And this was something that was revolutionary. They thought, oh, if we just put the two elements together, we're going to have the same material. Well, that's not always the case. So we have carbon monoxide, we have carbon dioxide. They would have different ratios. They would have different definite proportions. So we had to call this a different law. This is the law of multiple proportions. So here are Dalton's big understandings. And this makes sense. Again, everything is made up of atoms. He declared it, he gets credit for it. All atoms should have the same properties. We take that for granted now. That makes sense. If I have gold, it's going to look like gold. But back then, someone had to write it down in the 1800s. They just weren't worried about these scientific principles. They were in an age of enlightenment. Atoms are different from one another. Their compositions of compounds can be made from the composition of, or the combination of more than one atom. And this happens through a chemical reaction. So he has 5 big principles. But overarching, here's the big deal. We are starting now moving towards analyzing what is an atom. So Dalton has this idea that atoms are these solid single spheres. He wasn't right, but that's his concept, is that everything in the world is made up of small little bitty billiard balls. Each billiard ball has a different color, a different number on it. Every element has a different symbol upon it, he thought. He actually came up with a few periodic table symbols. We don't use them much today, but just so that you see the foreground, it's starting here. He's starting to write some letters down to represent elements. So we're starting to get there in the early 1800s. Now let's move 100 years forward. We're almost to the 1900s, and we've got J.J. Thomson. J.J. Thomson does an experiment with neon. They called it a cathode ray tube, but it's neon. And what he did is he put a magnet on the neon and he was able to bend the light. Well, how in the world can you bend the light if it's a solid sphere of the same material? That means there has to be some charges in there. So he comes up with the idea that there are electrons embedded inside of these solid spheres. So J.J. Thomson is now responsible for understanding the principle of electrons. He comes up with the idea. He called it the plum pudding model. So imagine a blueberry muffin. It's got sprinkled inside of it blueberries. If you want to say a chocolate chip muffin, that's fine. That's J.J. Thomson's idea. So here is his experiment. Again, he is using neon. And he is bending the light with magnets. That tells him there had to be some magnetic positive, negative charge inside the atom. So he then takes that and he theorizes it into the plum pudding model, which says solid spheres and it has electrons dancing around it. So we've got Dalton, we've got Thomson. Let's move on. We've got about a decade later, we've got Ernest Rutherford. His gold foil experiment takes us from a solid sphere with particles inside to now the nucleus. His experiment, he expected to shoot radiation at atoms and it would bounce back at him. In fact, what happened is the radiation passed through. That can only happen if there is space inside the atom. So what Ernest Rutherford understands is that through his gold foil experiment, that the atom is mostly empty space. So there is a nucleus that has all the mass in the middle, and these electrons are not just floating around the solid mass, they're floating around space around it. So we're starting to understand the atom looks a little bit more like what we expect it to. We come up to Millikan. And again, we're in about the same decade. So now we understand electrons. We got to figure out what their charge is. So Millikan does an experiment called the oil drop experiment, and he calculates what the mass as well as what the charge of electrons are. So that helps us to now understand how we can count protons and electrons through Millikan's experiment. So now Millikan, through his oil drop experiment, starts to think that we have a positive nucleus in the middle and we have negative electrons floating around. We're starting to see a picture. This starts to kind of look like an atom that you and I know. We come to Bohr, B-O-H-R. Bohr does an experiment with light. Not only like Rutherford, who was J.J. Thomson, who was bending light, he was allowing a prism to bend the light, to separate the light into the individual colors. He was then able to understand that the different colors have different wavelengths and they have different energy amounts. Well, that's only possible if the electrons are circling around the nucleus at different heights. So Bohr comes up with the idea of energy levels. So let me take you back. Here we are with Millikan. Notice there's no structure to the electrons. Now with Bohr, what we're going to see through his light experiments is that we have electrons that exist at specific distances from the nucleus. We call these energy levels. The further you get away, more energy you have, the closer you are, the closer the attraction from the positive to the negative, the harder it is to remove those electrons. The easier it is to remove electrons that are further away. Last pieces of the puzzle. James Chadwick. He built on Rutherford's gold foil experiment, but this time he says, I'm gonna capture some of those particles in a thick wax, a paraffin wax. He shoots his radiation through particles of beryllium as well as the wax, and what he finds out on the other side is that the mass before doesn't equal the mass after. So there had to be something that got captured by the wax. And those happen to be the neutrally charged neutrons. So James Chadwick, a couple of decades later, has finished now our idea of the model of the atom. He's now put us with protons, we discovered sort of through Rutherford, and then we have Thomson, who comes up with the electrons, and we have James Chadwick, who comes up with the neutrons. So a complete story is that here, sometime around the World War II era, we started to then see that the electrons are not quite as fixed, or like as Bohr had envisioned them. They're more of a hazy cloud. So this is how we idealize our atom models. But the reality is it's a little bit more hazy. We don't have definite locations of the electrons. So here's where we are. This is our history of the model of the atom. Dalton to J.J. Thomson to Rutherford to Bohr. And then there's a group of scientists, most notably credited here somewhere with Schrodinger. You might know him from psychology class where he does Schrodinger's cat. You can never predict, nor can you tell me where the location of the electron is or the safety of a cat in a box with poison. Something you can investigate on your own. Let's take a second here and let's have a quiz. Take 1 stinking minute. Look back on your notes, and Stafford, you're gonna lead us. Forge, I will come to you next. Bend at home here, North, Spotsy, and King George, read your question and be ready to go with some discussion, class. It could be individual, I don't care how we go about this. And Stafford, if you are ready, jump in at any time. I don't have my speaker on for you guys. Did you guys say it? I don't know. Hold on. Let me see. My speaker's not working, so I'm betting that you said something.
We did not hear anything at Forge.
Okay, so it's not me. Okay, or it is. Well, no, it's not. It's always me. It's not you. All right, Stafford, what you got? What did Thompson discover?
Electron.
Electrons. Okay, I lost my place on here. Where was I? Oh, here we are. Okay, so we got electrons for Thomson. Great. Forge. What do we got? What did the Bohr model look like?
It would look like there would be a nucleus and protons in the middle, and there would be like the different levels of the distance that the electrons would be away from the nucleus. But-
Perfect. Oh, but, okay, go ahead, but.
Say, but they didn't have the neutrons yet, or yeah, the neutrons yet because it's.
Ooh. I like your detail there. You're right, we didn't have a neutron yet. All right, Riverbend, what did Dalton say about the atom? Go
I
ahead.
came up with the law of multiple proportions, and you can have multiple atoms creating compounds.
Okay, law of multiple proportions, and what else did you come up with?
Atoms are the smallest particle that everything's made up of, and they're solid.
And everything is made up of solid atoms. You're absolutely right. All right, North. Chadwick, Forge mentioned this, but go ahead, North. Let's fill in the puzzle piece. What did Chadwick come up with, North?
He discovered neutrons.
The neutrons is correct. All right, Spotsy, what was the name of Rutherford's experiment?
It was known as the gold foil experiment.
Whoop, whoop. All right, King George, bring us home. The law of definite proportions means what? You got the hardest one.
Whenever you put into a chemical reaction, your ratios will stay the same.
That's exactly right. Great job, team. I'm so impressed. I'm so proud. I want to be just like you when I grow up. All right, here we go. We're moving on. Last details. So, atomic number. Here is where you gotta drill down and you gotta start focusing. This is where we learn chemistry 101. If you don't have this foundation, you will be lost for some time to come. So please, lean an ear in and let's make certain that we understand the difference between some very similar terms that are going to come your way. We start with the basic idea of the atomic number. The atomic number is the number of protons. Now, coincidentally, protons and electrons are going to equal one another. Now, that's a good thing because we want to hold the atom together. And so we want to have the same number of protons that we do electrons. But it's not an absolute rule. It's not always that protons and electrons are going to be the same. In fact, after this week, we're gonna quickly get into something called an ion, and that's all gonna change. So get used to it only superficial level here. So in other words, if I look at sodium, it is element number 11 on the periodic table. You should be able to tell me today that it has 11 protons and it has 11 electrons. That's it. That's your atomic number. But we're going to move away from that very, very soon. So don't get too accustomed to that idea. Now, here is where we already start getting confusing for a good novice student. The atomic number sounds just like mass number, but you have to be able to distinguish the two. Atomic number only gives you protons, where the mass number gives you protons plus neutrons. So the mass number is equal to protons plus neutrons. Essentially, this is the mass of the nucleus. Now that changes properties, just like it does in you. If you were to be 100 pounds more than you are today, you would have different properties. Not only would your mass have changed, but you would probably see some other conditions change in your body as well. And the same thing happens for atoms. If they get too heavy, if they have too many neutrons, they start to get sick and they start to become radioactive and they start to fall apart. So there is a nice, happy, specific ratio. It usually falls somewhere in between 1.5 and 2 neutrons that they can stay healthy. If they go below that or they go above that, there seems to be something that does not allow them to stay together as a normal atom and they start becoming radioactive and falling apart. So now we have established that it's possible for us to have atoms with different numbers of neutrons. We will call these isotopes. Atoms with different protons atoms with different neutrons get different names. They have different properties. Now, the name of the element cannot change. If I have 11 protons, it is always sodium. 11 protons is always sodium. But it could be possible for us to have 12 neutrons or for us to have 11 neutrons. Well, we need to be able to distinguish between sodium that has 11 and sodium that has 12 neutrons. So we call them isotopes of one another. Now notice, the protons didn't change in this example below. The electrons did not change. The only thing that changed is the number of neutrons. Now, this just so happens that these are specific, these are the only types of isotopes that get some very, very specific names. They're hydrogen. So we have protium, we have deuterium, and we have tritium. All other isotopes take on a nuclear symbol notation so we can distinguish them. If you look at the pattern that is established on the names outside of those very specific protium, deuterium, and tritium names, it's the name of the element, a dash, and the number following it is the mass number. So that mass number is protons plus neutrons. Now we always know if we're counting for hydrogen that it has 1 proton. You can't change the number of protons. You will change the element if you change the protons. So in each of these cases, the protons equals 1. So that's why for hydrogen 1, it only has 1 as its mass number. Hydrogen 2, it has a proton and a neutron. If you add those together, you're going to get hydrogen 2. And then finally, hydrogen 3 over here, well, it has 3 particles in the nucleus. It has 1 proton, 2 neutrons. Add them together, you get 3. All 3 of these are isotopes of one another. They are all hydrogen, but they have different mass numbers, so they get different names. One of them is hydrogen 1, hydrogen 2, and hydrogen 3. So Now, what if we don't want to write out their names? What if we just want to use their symbol? Notice down below here, those same three element isotopes are down here. Notice how that mass number has now transferred to the upper left corner. So the mass number will be represented in the upper left corner of a symbol off the periodic table. You can choose any element, but you're gonna have to have a little bit more information. You're gonna have to know what its mass number is for you to write this nuclear symbol. The bottom left number, that's its atomic number. That doesn't change. Carbon is element 6, it has 6 protons, so it is going to be the same consistently. The number at the top left is the mass number, protons plus neutrons. The number in the bottom left corner is the atomic number, that's the number of protons. Now let's remind you where those come from. They come from the periodic table. If we were to look at one box off the periodic table, so if I'm going to take oxygen, right there. Oxygen is element number 8. That means it has an atomic number of 8. That means it has 8 protons. But here's where all good first-year chemists get messed up. And this is where we're going to leave you today. We're going to do a quick quiz, but this is the last little detail. Do not confuse this number down here. It has a distinct different name. Don't say, oh, that's the mass number. It's not. It's called an atomic mass. You will see some good chemists, not myself, but maybe Mr. Rybach, Dr. Peppers, Poe, Diaz, Britt, you might see some of those guys. They accidentally may call it the atomic weight. Don't get freaked out. The atomic mass and the atomic weight, they are synonymous with one another. It is different. The atomic mass is the average weight of all the isotopes. So my goodness, I have already thrown like 4 or 5 different terms at you that you're going to have to sort out. That's tough. I get that. But with a little bit of review, you're going to be fine. So let's remember, atomic mass is an average. Mass number is a formula, protons plus neutrons. Atomic number is the number of protons, which is sometimes equal to electrons. And then there's this nuclear symbol, and then there's the name. Isotopes. There's a lot of things that sound, and we haven't even got to ions yet. So start off the year right, review your notes just a little bit, and let's practice right now. So here we go. Right down the line, straight Stafford, Forge, Bend, North, Stavatsi, and King George. This is the last thing I wish to share with you. Stafford, when you are ready, we are ready for you. You're going to tell us the number of protons in nitrogen 15. That's its isotope name. Forge, you're going to tell me how many neutrons are in sulfur 37. Bend, you are going to tell me what's the name of the isotope that has 20 protons and 26 neutrons. North, look at those symbols. Spatsy, look at those symbols. Tell me the neutrons and the protons. And then King George, you get screwed again. You got the hard one again. What is the name of barium isotope if it has 82 neutrons, but you have the most time? So we're ready for Stafford when you are ready, Stafford. If you want to tell us the number of protons.
15.
How'd you come up with 7?
What's it called? The atomic number on the periodic table.
Oh, that's right. Good job, Stafford. Good job. All right, Forge, let's pick it up. How many neutrons?
How many neutrons? No,
That's not very.
16 minus 37, 19. No. 21. Final-
Yay, Matt, we can do it. Yay!
Final
Where did
answer,
that 16 come from? Where did the 16 come from?
37 minus the atomic number.
That's it. Yes, minus the atomic number. The atomic number is protons. In fact, we
16.
said bend. All right. What's the name if you have 20 protons, Drew?
Calcium.
Calcium is correct. All right. Help us out now. Someone else. What's the name of this isotope? So it's calcium, but it's got 26 neutrons. So where do we go to get the other part of this name?
You add it's just the mass number.
It's the mass number. So what is that mass number? That's exactly right. So we got calcium 46 here. North, how many neutrons are in cobalt 60?
33.
That is correct. You just subtracted those two numbers. Top minus bottom gives you number of neutrons because that top number is protons, neutrons. Bottom number is protons. All right, Spotsy, how many protons in selenium? This is so easy.
How many you got?
70. Oh, wait, 34.
I heard it. 34 is correct. Good. King George, last detail. What's the name of a barium isotope if it has 82 neutrons? So we know it's going to be barium something.
Barium 138.
Oh, barium what?
138.
Yeah, you rock, sister. Sir? Okay, sir. Sorry. You are a superstar. Woo! All right, my friends, I've shared with you far too much, but I'm hopeful that you feel confident you can name those scientists and you have a groundwork for being able to talk about how to determine protons, neutrons, and sort of electrons right now. Okay, so thank you very much. I hope you have a great afternoon. Go out there and do some practice. We'll see you again soon. Bye. I'm trying to figure out how to close down.